Tonight, we're going to talk about the biggest star in the universe. But before we get there, we need to start somewhere smaller. We need to start with our sun. Picture the sun for a moment. It's about 865,000 miles across. That's so wide that roughly 1.3 million Earths could fit inside it. The light leaving its surface right now will take 8 minutes to reach you. 8 minutes traveling at 186,000 miles per second. That's not a small object. By any reasonable human standard, it's an incomprehensible one. And yet the sun barely registers on the scale we're about to talk about. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. There are stars out there so large that if you dropped one at the center of our solar system, it wouldn't just swallow Earth. It wouldn't just swallow Mars. It would swallow Jupiter. In some cases, it would keep going past Saturn. The sun, that object that seems to fill the sky and drives every living thing on this planet, would disappear inside it without making a noticeable difference to the star's volume. Think about that for a second. So which star actually holds the record? What is the single largest known object of its type in the universe? Here's where things get genuinely interesting and a little strange. The answer has changed. More than once. Stars that were confidently listed as the largest known have been remeasured and knocked down dramatically. A star that was considered the definitive record holder for years turned out to be less than half the size people thought. And the star currently sitting at the top of the list is so enormous that it exceeds what our best theoretical models say should even be possible. Either the measurements are off, or the theory is wrong. Possibly both. This is not a settled question. It's an active one. And the closer you look at it, the more unsettling it gets. We're going to work through the whole picture tonight. We'll start with the sun as a baseline, then move through some of the most extreme stars ever found, building toward what currently holds the record and what that actually means in physical terms. We'll talk about why measuring these objects is so genuinely difficult, why the leaderboard keeps shifting, and what it would actually look like to stand, hypothetically, near one of these things. Some of these numbers are going to stop making sense, not because the science is complicated, but because the scale exceeds anything the human brain evolved to process. A star wider than the distance from the sun to Saturn isn't something you can picture. What you can do is keep layering comparisons until something starts to click. If you find this kind of thing as fascinating as we do, take a second to subscribe or like the video. It's a small gesture, but it expands how many people discover this channel and want to spend their time thinking about things like the largest objects in the known universe. We appreciate it. There's one more thing worth saying before we get into the details. The stars we're going to talk about are not hypothetical. They're not science fiction. They exist right now, burning in real locations in the sky. Some of them visible with a telescope. Some of them buried so deep in the plane of the galaxy that only infrared light can reach us through the dust. They are out there tonight, as you're watching this, in various stages of a slow and violent death. Red, enormous, unstable, and in some cases doing things we've never observed before in a star of their size. That's the kind of territory we're heading into. Genuinely strange, actively debated, and bigger in every sense than most people realize. Now let's begin. Let's start with what you already know, or think you know, about the sun. You've seen it your entire life. It rises every morning, it sets every evening, and on a clear day it's bright enough to damage your eyes if you look directly at it. It feels enormous. It dominates the sky. And compared to anything you've ever stood next to, it genuinely is enormous. The sun is about 865,000 miles across. That's 1.4 million kilometers in diameter. If you hollowed it out and started filling it with planets the size of Earth, you could fit roughly 1.3 million of them inside before you ran out of room. Think about that for a second. Every continent, every ocean, every mountain range on Earth, multiplied by 1.3 million, and you still haven't filled the sun. The light leaving the sun's surface right now will reach your eyes in about 8 minutes. That's the distance we're talking about. 8 minutes at 186,000 miles per second. If you drove a car from the Earth to the sun at highway speed, the trip would take about 170 years. The sun isn't close. It just looks close because there's nothing between us and it to give you a sense of scale. From Earth's surface, the sun appears as a disk about the same apparent size as the moon. That's a coincidence of geometry. The sun is about 400 times wider than the moon and also about 400 times farther away, which makes them look almost identical in the sky. That coincidence is what makes solar eclipses possible. But that apparent size is deceptive. The sun you see at arm's length, covered completely by your thumb, is a ball of plasma so hot at its core that the temperature reaches about 27 million degrees Fahrenheit. It's been burning for 4.6 billion years and has enough hydrogen fuel left to keep going for another 5 billion. It converts roughly 600 million tons of hydrogen into helium every single second. The quiet yellow disk you see at sunrise is one of the most violent objects in the solar system. So when astronomers need to compare stars to each other, the sun is the obvious baseline. They measure stellar size in units called solar radii. One solar radius is the distance from the center of the sun to its surface, about 432,000 miles, or 696,000 kilometers. Every star you'll hear about from this point forward gets measured against that number. A star with a radius of 10 solar radii is 10 times wider than the sun. A star at 500 solar radii is 500 times wider. The sun becomes, quite literally, the yardstick for the cosmos. It's the unit of measurement precisely because it's familiar and well-studied, because we've been measuring it for centuries and the numbers are solid. Everything else gets scaled against it. Here's where things get uncomfortable, though. By every meaningful measure, our sun is average, not impressive, not extreme, just average. It's classified as a G-type main sequence star, a yellow dwarf, which puts it squarely in the middle of the stellar population. It's not the brightest kind of star. It's not the hottest. It's not the most massive. If you sorted all the stars in the Milky Way by size, the sun would fall somewhere unremarkable in the distribution. There are stars smaller and dimmer, red dwarfs that barely qualify, cool embers of stars that could fit comfortably inside the orbit of Jupiter. There are also stars at the other end of the spectrum that make the sun look like a rounding error. The Milky Way alone contains somewhere between 200 and 400 billion stars. The vast majority of them are smaller and cooler than the sun. Red dwarfs make up an estimated 70 to 75% of all stars in the galaxy. So by that measure, the sun is actually above average. But the stars above the sun on the size scale, the truly large ones, are so much larger that the gap becomes genuinely difficult to process. We're not talking about stars that are twice the sun's radius, or 5 times, or even 50 times. We're talking about stars that are hundreds of times the sun's radius, thousands of times. Stars so large that if you replaced our sun with one of them, the surface of that star would reach past the orbit of Mars, past the asteroid belt, past Jupiter. That's not a poetic exaggeration, that's the actual math. And it's where the sun as baseline framing stops being just a convenient unit of measurement and starts being genuinely useful for understanding what you're looking at. When someone says a star has a radius of 1,500 solar radii, you now have a reference point. You know the sun. You know how far away it is, how large it is, how incomprehensibly large it already is by any human standard. Now multiply that by 1,500. That number should feel wrong in a way that's hard to shake. And once you understand that, the stars that come next start to seem almost impossible. To understand what makes a star enormous, you first have to understand how stars get that way. Stars are not static objects. They're engines running on nuclear fuel, and like any engine, what they do depends entirely on what's left in the tank. For most of a star's life, that fuel is hydrogen. Deep in the core, hydrogen atoms are forced together under crushing pressure and temperature until they fuse into helium, releasing enormous amounts of energy in the process. That energy pushes outward. Gravity pulls inward. The two forces balance, and the star holds its shape. Astronomers call this the main sequence, the long, stable phase where a star just burns and burns and burns. Our sun has been on the main sequence for about 4.6 billion years. It has roughly another 5 billion to go. But not every star gets that kind of time. Here's where mass becomes the critical variable. A more massive star has more fuel, but it also has more gravity compressing its core. That extra compression means higher pressures and higher temperatures, which means the fusion reactions run faster. Much faster. A star 10 times the mass of the sun doesn't live 10 times as long. It lives something like 100 times shorter. A star with 20 or 30 solar masses might exhaust its hydrogen fuel in only a few million years. These are stars that burn bright and die young, cosmically speaking. So what happens when the hydrogen runs out? The core, now composed mostly of helium, can no longer sustain fusion. It starts to contract. As it contracts, it heats up. Meanwhile, there's still a thin shell of hydrogen around the core that hasn't been used yet, and the rising temperatures ignite that shell. The shell burning dumps enormous amounts of energy into the star's outer layers. Those outer layers respond by expanding, not slowly, but dramatically. The star swells outward by hundreds of times its original size. As it expands, its surface cools. The surface temperature drops from something like 6,000 Kelvin down to below 4,100 Kelvin. And at those temperatures, the star glows red. The transition occurs on surprisingly short timescales. Where hydrogen burning might sustain a star for billions of years, the red supergiant phase unfolds over mere millions. For massive stars, this red supergiant phase persists for only a few 100,000 years before the core fuses heavier elements. The star's behavior becomes increasingly unstable as it exhausts each fuel source. Pressure and temperature in the core oscillate wildly. Contractions and reignitions then occur rapidly as iron elements begin forming in successive layers. What unfolds is not a gentle fade, but a frantic series of nuclear reactions. Each burns faster than the last. Each one lasts progressively shorter than the one before it. This is what a red supergiant is. It's a massive star in the late stages of its life, bloated beyond anything on the main sequence, cooler at its surface than it's ever been, and yet still pumping out extraordinary amounts of light. That last part seems counterintuitive. How can something cooler be so bright? The answer is surface area. Luminosity depends on both temperature and size. If you expand a star's radius by a factor of 1,000, you increase its surface area by a factor of 1,000,000. Even with a lower temperature, 1,000,000 times more surface area means a vastly higher total energy output. Red supergiants are typically tens of thousands to hundreds of thousands of times more luminous than the Sun. The size compensates for the coolness, and then some. Their spectral types are K and M, the same classification system used for cooler, smaller stars, but at a completely different scale. Surface temperatures run from around 3,200 to 4,100 Kelvin, compared to the Sun's 5,778 Kelvin. That's why they look red or deep orange when you observe them. The color is a direct readout of the surface temperature. Cooler stars glow red. Hotter stars glow blue or white. Red supergiants sit at the cool end of that spectrum, which is why it can feel backwards that the biggest stars in the universe are also among the reddest and coolest. Now, you might wonder whether this process can go on indefinitely. Can a star just keep expanding forever? The answer is no, and the reason why comes down to a concept called the Hayashi limit. As a star's outer envelope expands, something else is happening at the same time. The star is generating radiation pressure, the outward push from all the photons pouring out of its interior. In a smaller, denser star, gravity comfortably wins that tug of war. But as the star grows larger and more extended, gravity at the surface gets weaker. The outer layers are now so far from the dense core that the inward gravitational pull on them is dramatically reduced. At some point, the radiation pressure starts to approach the gravitational pull holding the star together. Theory says that around 1,500 solar radii, that balance breaks down. A star approaching this size is generating so much outward radiation pressure that it begins to shed its outer layers into space. The envelope doesn't just sit there, it gets blown off. The star can't hold itself together at that size. Any attempt to grow beyond roughly 1,500 solar radii should result in the star losing mass faster than it can accumulate it, effectively capping how big it can get. This is the Hayashi limit in its practical form. It's not a hard wall so much as a point of instability, a threshold beyond which the physics of a stable stellar envelope essentially breaks down. Stars near this boundary tend to be violently variable, pulsating, and shedding enormous amounts of material. They're not stable in any comfortable sense. They're heaving. What's remarkable is that several stars we've identified appear to sit right at this boundary or even beyond it. Either the measurements are off, which is genuinely possible, and we'll get into that, or some stars are managing to exceed what current theory says should be possible. Both options are interesting. One means our instruments and methods have limits we need to account for. The other means our theoretical models of stellar structure are missing something fundamental. Either way, the Hayashi limit gives you a target to keep in mind. It represents physics drawing a line and saying, this far, no further. That theoretical ceiling becomes important later because some of the stars we're going to look at appear to crash right through it. Here's something that surprises a lot of people. We actually don't know the exact size of most of the largest stars. That might sound like a strange admission. We live in an era where we can image a black hole 55 million light-years away, where we can detect gravitational waves from colliding neutron stars. Surely measuring the diameter of a star isn't that hard. But it is. It genuinely is. And understanding why tells you something important about what every number you're about to hear actually means. Let's start with the most direct method: stellar interferometry. The basic idea is to measure a star's angular diameter, how wide it appears in the sky when viewed from Earth. This sounds straightforward, but think about what you're actually dealing with. Even the nearest stars beyond our sun appear as nothing more than pinpoints of light through even the most powerful conventional telescopes. The angular sizes are almost unimaginably small, fractions of a thousandth of an arcsecond for most of them. To measure something that tiny, astronomers have to combine light from multiple telescopes separated by large distances, using the interference patterns those light waves create to reconstruct an image with much higher resolution than any single telescope could achieve. This works, but it only works well for stars that are relatively close and relatively large in angular terms. For a red supergiant sitting tens of thousands of light years away, buried near the center of the galaxy, it becomes extremely difficult. The angular diameter is so small that even interferometry struggles to nail it down precisely. So for most of the giant stars we're going to talk about, astronomers rely on indirect methods. They measure the star's luminosity, how much total energy it's putting out, and its surface temperature derived from its spectrum, the specific mix of wavelengths in its light. Then they use a fundamental relationship in physics called the Stefan-Boltzmann law, which connects luminosity, temperature, and size. If you know how bright a star is and how hot its surface is, you can calculate how large its surface area must be, and from that, its radius. This works in theory. In practice, getting accurate luminosity and temperature measurements introduces its own chain of uncertainties. Dust between Earth and the star absorbs and reddens the light, making the star appear dimmer and cooler than it actually is. Correcting for that dust requires its own set of assumptions. But here's the part that really matters. Every indirect method of measuring a star's size depends first and most critically on knowing how far away the star is. And getting the distance right is where things can go badly wrong. The relationship is direct. If you think a star is twice as far away as it actually is, you'll calculate that it's putting out 4 times as much total light as it really is, because light spreads out according to the inverse square law. And if you overestimate the luminosity, you'll overestimate the radius. Get the distance wrong by a significant margin, and the calculated size can be off by a factor of 2 or more. Not by a small percentage, by half or double. This is not a hypothetical problem. It happened with one of the most famous stars in this entire conversation. For years, UY Scuti was widely celebrated as the largest known star in the universe. The measurements placed its radius at roughly 1,700 solar radii. That number was repeated everywhere. It spread across textbooks, videos, articles, science websites. The largest star in the universe, nearly 1,700 times wider than our Sun. Then better distance data arrived. The Gaia Space Telescope, launched by the European Space Agency in 2013, spent years systematically mapping the positions and distances of over 1 billion stars with extraordinary precision. When astronomers applied improved distance measurements to UY Scuti, the radius dropped to somewhere around 775 solar radii, less than half the previous estimate. A star that was supposed to be nearly 1,700 times the Sun's width turned out to be closer to 775. That's not a minor correction. That's a fundamental revision. Now, 775 solar radii is still enormous. Think about what that means in practical terms. Even at that revised size, if UY Scuti replaced our Sun in the center of our solar system, it would extend past the orbit of Jupiter. It would swallow every inner planet without a second thought. This is not a small star, but it's not the record holder it was thought to be. And the lesson here isn't that astronomers were sloppy. It's that measuring these objects is genuinely hard, and better tools produce better answers. There's a third method worth knowing about: eclipsing binaries. Some stars orbit each other, and when one passes in front of the other from our line of sight, the way the light dims and recovers tells you something precise about the physical dimensions of each star. These systems are incredibly useful as calibration tools. They give you size and mass measurements that don't depend on distance estimates in the same way. But most of the extreme giant stars we're interested in aren't conveniently paired in eclipsing binary systems. They're single stars, often isolated, surrounded by dust, far away. The calibration tools astronomers would most want to use often aren't available for the stars they most want to measure. What you end up with is this: a leaderboard of the universe's largest stars that shifts and updates as measurement techniques improve and as new data arrives. Stars get remeasured and drop in the rankings. Stars that were overlooked turn out to be larger than anything previously cataloged. The title of largest known star has changed hands multiple times within living memory. That's not a sign that the science is broken. It's a sign that it's working, that astronomers are willing to revise their conclusions when better evidence demands it. Which means every star we're about to discuss comes with an asterisk. For years, if you asked anyone with even a passing interest in astronomy which star was the biggest, the answer was UY Scuti. It showed up in videos, infographics, classroom presentations, and science magazines. The comparison images were everywhere, our sun reduced to a tiny dot next to this enormous red sphere. UY Scuti became the go-to answer, the reliable fact you could drop into a conversation to make someone's jaw fall open. And for a while, the science seemed to back it up completely. Measurements put it at roughly 1,708 solar radii, more than 1,700 times wider than our sun. That number circulated widely, got repeated millions of times, and hardened into something that felt like settled fact, which is exactly what makes what happened next so instructive. Let's talk about what UY Scuti actually is. It sits roughly 9,500 light-years away in the constellation Scutum, relatively close to the dense central regions of the Milky Way. That part of the galaxy is packed with stars, gas, and dust. That makes it both a productive hunting ground for large stars and a genuinely difficult environment to measure things in. UY Scuti is a red supergiant, specifically a pulsating variable star, meaning it expands and contracts over time, its brightness rising and falling in a cycle. Its surface temperature sits at around 3,092 degrees Celsius. That's actually cooler than our sun's surface, which runs closer to 5,500 degrees. This is the paradox of red supergiants that we covered earlier. They're bigger, but they're cooler, and they glow that distinctive deep red because of it. Here's something that puts UY Scuti's age in sharp relief. The sun is about 4.6 billion years old and still has several billion years left. UY Scuti is somewhere between 10 and 20 million years old. That sounds like a long time, but on stellar timescales, it's extraordinarily brief. The reason is simple: the more massive a star is, the faster it burns through its fuel. UY Scuti is consuming itself at a rate so intense that it's already approaching the end of its life despite being cosmically young. It's likely in the final stages before a supernova event, puffed up to enormous size as its core exhausts its fuel and the outer layers expand outward. That expansion is precisely what makes it so large, and also what makes it unstable. The original measurements that put UY Scuti at 1,708 solar radii came from calculations using its apparent brightness, its estimated temperature, critically, its assumed distance. And that last piece is where the problem was hiding. Determining the distance to a star 9,500 light-years away is not straightforward. The further away something is, the harder it is to pin down precisely. Astronomers used the best available data at the time. 1,708 solar radii was the honest result of that work. But the distance estimate carried real uncertainty. When the distance is wrong, the size calculation built on top of it is wrong too. Then came Gaia. The European Space Agency launched the Gaia spacecraft in 2013 with a mission to map the positions and distances of more than 1 billion stars with unprecedented accuracy. It measured parallax, the tiny apparent shift in a star's position as Earth moves around the Sun, at a precision that earlier instruments simply couldn't match. When Gaia's data was applied to UY Scuti, the distance estimate changed. And when the distance changed, the calculated radius changed with it. The revised figure landed at around 775 solar radii, less than half of what had been reported before. In one stroke, UY Scuti went from unambiguous record holder to a star that doesn't even crack the top of the current list. Think about what a revision like that means for a number that had been repeated as fact for years. Every video that described UY Scuti as 1.700 times the size of the Sun was now overstating its size by more than 100%. Every infographic showing it dwarfing the solar system was drawn to the wrong scale. None of that was the result of careless science. It was the result of measuring a difficult object with the best tools available. Then those tools getting better. That's not a failure. That's the process working. But it does illustrate something important about how you should hold any single data point in astronomy, especially one involving a star thousands of light years away. The number is always the best current estimate. It is not a guarantee. So what does 775 solar radii actually mean? Even the revised figure is genuinely difficult to grasp. If UY Scuti replaced our Sun at the center of the solar system, its surface would extend well beyond the orbit of Jupiter. Mercury, Venus, Earth, Mars, the asteroid belt, all of it would be inside the star. Jupiter itself orbits the Sun at about 5.2 astronomical units. UY Scuti at 775 solar radii has a radius of roughly 1.07 astronomical units. That means it would fill the space out past Earth's orbit and push toward Mars. Some estimates push the outer edge closer to or slightly past Jupiter, depending on where in its pulsation cycle the star happens to be. Either way, the number is staggering. We're talking about an object larger than the entire inner solar system, reduced to less than half its previously reported size. It's still this large. That pulsation matters here. UY Scuti's radius isn't fixed. It swells and contracts as the star cycles through its variability. That means any single measurement captures only a snapshot. The 775 solar radii figure represents a best estimate based on current data. But the star itself is actively changing size on timescales we can observe. This variability complicates every measurement and is part of why pinning down an exact radius for a star like this is so hard. You're not measuring a static object. You're trying to measure something that is constantly in motion. What the story of UY Scuti really teaches is that the leaderboard of extreme stars is not a stable document. It shifts when technology improves. It shifts when new data arrives. Stars that held the record for decades can be revised dramatically by a single better measurement of their distance. The universe doesn't change. Our picture of it does. And sometimes that picture changes fast. UY Scuti was the largest known star for long enough that the claim became embedded in popular science culture, repeated so often it felt permanent. Then Gaia came along and the number dropped by more than half. It's still one of the largest stars ever found. It just isn't the one at the top of the list anymore. Most of the stars we're going to talk about tonight are invisible to the naked eye, so distant and buried in the plane of the galaxy that you'd need a serious telescope to find them. But there's one red supergiant that's different. One that you've almost certainly seen without knowing what you were looking at. Step outside on a clear winter night, find the constellation Orion, and look at his right shoulder. That orange-red star, slightly dimmer than the blue-white stars around it, is Betelgeuse. It's sitting there in plain view, about 548 light-years away, and it is one of the largest and most unstable stars in our corner of the galaxy. 548 light-years sounds like a lot. It is a lot, but compared to UY Scuti at 9,500 light-years, or Stevenson 218 at nearly 19,000 light-years, Betelgeuse is practically a neighbor. That proximity is part of why we know so much about it. Astronomers have been able to study it in extraordinary detail, and what they've found is a star that is enormous, volatile, and running out of time. Let's talk about the size. Betelgeuse has a radius of roughly 764 times that of the Sun. But here's the thing, it doesn't hold still. Betelgeuse is a variable star, meaning it pulses and heaves, expanding and contracting over cycles that last months or years. At its smallest, its radius drops to around 550 solar radii. At its largest, it swells to somewhere near 920 solar radii. The star is literally breathing, though on a scale that makes breathing the wrong word for it. The entire surface surges outward and then pulls back, and the change in size between its minimum and maximum is larger than the distance from our Sun to Earth. Now put that in solar system terms. If you pulled our Sun out of the center of the solar system and dropped Betelgeuse in its place, the surface of the star would extend past the orbits of Mercury, Venus, Earth, and Mars. You'd lose all 4 inner planets, swallowed completely. The surface would push outward toward Jupiter's orbit, stopping somewhere in that range depending on which phase of the pulse cycle you caught it in. Everything inside that radius, every terrestrial planet, the asteroid belt, everything, gone. Betelgeuse isn't a distant abstract number. It's a volume of space large enough to consume the neighborhood where we live without noticing. Its mass is around 15 times that of our Sun. That's worth pausing on, because there's a relationship here that will come up again later in this video. Betelgeuse is 764 times larger than the Sun in radius, but only about 15 times more massive. It's not dense, it's expanded. The outer layers have ballooned outward so dramatically that the average density of the star is a tiny fraction of what it was when it was younger. The outer envelope of Betelgeuse is, in some regions, thinner than the best vacuum we've ever manufactured in a laboratory on Earth. It's enormous, but it's not heavy in the way you'd expect something enormous to be. Betelgeuse is also old, at least in stellar terms. A star 15 times the mass of the Sun burns through its hydrogen fuel at a ferocious rate. Where our Sun will live for around 10 billion years total, Betelgeuse is only about 8 to 10 million years old and is already approaching the end. It's fusing helium in its core. It's already a red supergiant. It is, by any reasonable measure, dying. And then, in late 2019, it started doing something strange. Betelgeuse began to dim. Not just the normal variation astronomers had tracked for decades, something far more dramatic. By early 2020, the star had faded by roughly 60% of its normal brightness. To the naked eye, it had dropped from one of the brightest stars in the sky to something much harder to spot. Astronomers noticed immediately. So did the general public. The coverage was intense. The question being asked everywhere was whether Betelgeuse was about to go supernova. This event became known as the Great Dimming. And the speculation was not unreasonable. A red supergiant fading that rapidly and that dramatically is exactly the kind of behavior you might expect from a star in its final death throes. Betelgeuse was already known to be near the end of its life. Was this it? It wasn't. What actually happened was something almost more interesting. The star had ejected a massive bubble of hot plasma from its surface, an outgassing event far larger than anything our sun produces. That plasma traveled outward, and as it moved away from the intense heat, it cooled. When it cooled, it condensed into dust. That dust cloud drifted between Betelgeuse and Earth, blocking a significant portion of the star's visible light. We weren't seeing the star dim. We were seeing a curtain of newly formed dust pass in front of it. Within a few months, the cloud dispersed and Betelgeuse returned to its normal brightness. The star had recovered, but it had given astronomers an unprecedented close-up look at how red supergiants shed material near the end of their lives. Since the Great Dimming, Betelgeuse has continued to behave unusually. Its pulsation cycles have been irregular. Some researchers believe the ejection event disrupted the star's normal convective rhythms. Others think this is just what a red supergiant looks like in its late evolutionary stages: chaotic, unpredictable, building towards something. That something is a supernova. There is no version of Betelgeuse's future where it doesn't explode. The current estimates put the event somewhere within the next 100,000 years, though some models suggest it could be considerably sooner than that. On cosmic timescales, 100,000 years is essentially now. On human timescales, it could be a very long wait, or it could happen before anyone reading a transcript of this video has grandchildren. When it does go supernova, the effect from Earth will be unlike anything any living person has ever witnessed. Betelgeuse is close enough that the explosion will be visible in broad daylight for weeks. At night, it will cast shadows. It will outshine the full moon. It will be a point of light so bright that people who don't follow astronomy at all will notice it and be unsettled by it. It will likely remain visible to the naked eye for months, possibly longer, slowly fading as the debris cloud expands and cools. And when it finally does explode, it will put on a show that no human alive today will ever forget. VY Canis Majoris is the kind of star that makes you question whether any of this is real. We just spent time with Betelgeuse, a star that would swallow Mercury, Venus, Earth, and Mars if you dropped it into the center of our solar system. That probably felt like enough. That probably felt like the upper boundary of what a star is allowed to be. It isn't. VY Canis Majoris sits in the constellation Canis Major, the Big Dog, about 3,900 light-years from Earth. It belongs to a class called red hypergiants, not supergiants, but hypergiants, which is what happens when even the word supergiant stops being sufficient. And its numbers don't just exceed Betelgeuse, they exceed your ability to hold them in your head. Let's start with the size. VY Canis Majoris has a radius of roughly 1,400 times that of our Sun. That translates to about 2 billion kilometers across. 2 billion. The Sun is roughly 1.4 million kilometers in diameter, which already seems incomprehensible. Now multiply that by 1,400. The resulting number is so large that it genuinely loses meaning if you just stare at it as a figure on a page. So let's try to do something more useful with it. If you replaced our Sun with VY Canis Majoris, its surface would extend past the orbit of Jupiter. Not Earth, not Mars. Jupiter. Every planet in the inner solar system, Mercury, Venus, Earth, Mars, would be submerged. The asteroid belt would be submerged. Jupiter itself would be sitting right at the edge of the star's outer atmosphere. Everything inside that boundary would simply cease to exist as anything other than part of VY Canis Majoris. And if you're struggling to feel that, Consider that Jupiter is more than 5 times farther from the Sun than we are. The Sun currently looks the size it does from Earth's distance. Now imagine standing at Jupiter's distance and still being inside the star. Volume is where these comparisons become almost comedic. More than 5 billion of our suns could fit inside VY Canis Majoris. 5 billion. Our sun, again, is already large enough to hold 1.3 million Earths. Stack that up. You could fill VY Canis Majoris with 5 billion objects, each of which could hold 1.3 million Earths. At some point, the math stops landing as anything meaningful, and that's actually the point. Human brains did not evolve to process scales like this. We evolved to track predators, estimate distances between trees, judge whether a river was crossable. Nothing in our evolutionary history prepared us for numbers like 5 billion solar volumes. If you want an analogy that at least gestures in the right direction, try this one. Imagine shrinking our sun down to the size of a basketball, about 24 centimeters across. On that same scale, VY Canis Majoris would be a sphere roughly 34 meters in diameter. That's taller than a 10 to 12-story building. The basketball is sitting somewhere inside a structure the height of a city block. That's the ratio. And even that analogy falls short, because we don't spend our daily lives standing next to 12-story spheres and feeling their scale physically. We just know they're tall. Now, what VY Canis Majoris actually is physically is just as extreme as its size. This is a star that is actively coming apart. It belongs to the hypergiant class, which places it above red supergiants in terms of both mass and luminosity. Hypergiants are rare. They burn through fuel at a ferocious rate, which is why they're also relatively short-lived. And they shed mass in enormous quantities, not steadily and quietly, but in violent outbursts that send enormous shells of material expanding into the space around them. VY Canis Majoris is surrounded by a thick, irregular nebula of ejected material. Astronomers can observe this nebulosity directly, arcs and clumps of gas and dust that the star has thrown off over tens of thousands of years. The star isn't just sitting there being large, it's unraveling. It's losing mass at a rate that would strip the outer layers of a smaller star entirely, and it's been doing this for a long time. The region around VY Canis Majoris is, in a sense, partly made of VY Canis Majoris, material that used to be part of the star now drifting away into the surrounding space. This mass loss is a sign of where VY Canis Majoris is in its life. It's approaching the end. Stars this size and this luminous don't get to live long. Their lifespans are measured in millions of years, not billions. And the instability that comes with the hypergiant phase, the mass shedding, the pulsations, the ejections, all of it points toward a final act that is going to be dramatic. Whether VY Canis Majoris ends in a core collapse supernova, a hypernova, or possibly a direct collapse without a visible explosion, the physics is pushing it towards something terminal. The classification of hypergiant is worth sitting with for a moment. In the hierarchy of stellar types, you have main sequence stars like our Sun, then giants, then supergiants, and then hypergiants at the extreme end. VY Canis Majoris sits in that last category. These are objects so luminous that the radiation pressure pushing outward on their outer layers is enormous, making them structurally unstable in ways that smaller stars never have to deal with. The boundary between supergiant and hypergiant isn't just a naming convention. It marks a real physical threshold where the star's own energy output starts working against its ability to hold itself together. So when you look at VY Canis Majoris, you're not just looking at something big. You're looking at something in a state of violent, prolonged self-destruction, enormous, luminous, unstable, surrounded by its own discarded material, and burning on a timeline that ends soon in cosmological terms. The numbers stopped making intuitive sense several paragraphs ago. That's fine. That's what this star does. And yet, even VY Canis Majoris is not the star at the top of this list. There's a part of our galaxy, toward the inner regions. In the constellation Scutum, where enormous stars congregate in a way that seems almost deliberate, not one or two red supergiants scattered randomly across a region of sky, 26 of them packed into a single cluster, all of them massive, all of them dying, all of them occupying the same small corner of the Milky Way. The cluster is called RSGC1, the Red Supergiant Cluster 1, and it is one of the most extreme concentrations of massive stars ever found in our galaxy. To understand why a place like RSGC1 exists, you have to think about how stars form in the first place. Stars don't usually form alone. They form in vast molecular clouds, enormous regions of gas and dust that collapse under their own gravity. When a particularly massive cloud collapses, it doesn't produce one star. It produces thousands, sometimes tens of thousands, all at roughly the same time. If the conditions are right, if the cloud is dense enough, if there's enough raw material, a significant fraction of these stars will be massive, and massive stars evolve fast. Within a few million years, they've burned through their hydrogen fuel and expanded into red supergiants. So what you end up with is a cluster where many of the heaviest stars reach the end of their lives almost simultaneously. RSGC1 is exactly that scenario playing out in real time. It's a stellar nursery that produced an extraordinary number of massive stars. Now those stars are all aging together. The cluster itself sits roughly 20,000 light-years from Earth deep in the inner galaxy. It was first cataloged in detail in the mid-2000s, and what researchers found was genuinely surprising. 26 confirmed red supergiants in one location is not something you expect. Most clusters contain a handful at most. RSGC1 has more of them than any other open cluster in the Milky Way. That makes it one of the most important places in the galaxy for studying what happens to massive stars at the end of their lives. And then there's RSGC1-F01. This is one of the cluster's standout members, and the numbers attached to it are difficult to process. Its radius is estimated somewhere between 1,436 and 1,530 solar radii. That range matters. We'll come back to why. But even at the lower end of the estimate, this star is operating in territory that should be physically impossible. Remember the Hayashi limit, the theoretical ceiling on how large a star can grow before radiation pressure overwhelms gravity and tears the star apart. That ceiling sits at around 1,500 solar radii. RSGC1-F01 is right at that boundary. It's a star that is either approaching the absolute physical limit for stellar size or already past it. Put it in solar system terms and the scale becomes visceral. If RSGC1-F01 replaced our Sun at the center of our solar system, its surface would extend outward past Mercury, past Venus, past Earth, past Mars, through the asteroid belt, out to the orbit of Jupiter. Everything you've ever seen in photographs of the planets, every probe we've ever launched into the inner solar system, every planet that has ever harbored any discussion of life would be inside this star, not orbiting it, inside it. That uncertainty in the radius measurement isn't a minor footnote. At these scales, a difference of 100 solar radii represents a physical distance larger than our entire solar system out to Mars. When astronomers measure a star like RSGC 1-F01, they're working with an object 20,000 light-years away, partially obscured by dust and gas in the inner galaxy, observable primarily in infrared because visible light can't punch through all that material. The angular size of the star on the sky is almost immeasurably small. Getting within a few percent of the true answer requires careful calibration of distance, temperature, and luminosity. Each of those measurements carries its own uncertainty. So when the published radius sits between 1,436 and 1,530 solar radii, what that range is telling you is that this star is somewhere in the neighborhood of the largest physically stable object that can exist, and we're not entirely sure which side of that line it's on. What makes RSGC-1 important isn't just the individual stars, it's what the cluster as a whole represents. Astronomers studying the upper boundary of stellar size need reference points. They need places where they can find multiple extreme stars in the same location, at the same distance, formed from the same original material, and compare them directly. RSGC-1 provides exactly that. When you have 26 red supergiants in one cluster, you can cross-check your measurements, calibrate your methods. Start to build a clearer picture of where the actual size limits are. The cluster is a natural laboratory for testing the physics of massive stellar evolution in a way that isolated stars simply can't provide. The constellation Scutum keeps appearing in this story. RSGC-1 is here. Stephenson 2-18, which we'll get to shortly, is also in Scutum, in a nearby cluster called Stephenson 2. This region of the sky, looking toward the inner Milky Way, is extraordinarily rich in massive stars. The conditions in the inner galaxy, higher stellar density, more molecular cloud material, a more active star formation history, appear to produce these extreme objects at a higher rate than the quieter outer regions of the disk. When you point a telescope toward Scutum and look in infrared, you're looking at one of the most violent and active regions of our galaxy, a place where the most massive stars form and the most extreme deaths happen. It's one of those places in the universe that makes you feel like the laws of physics are being pushed right to their edge. Then there's Stephenson 2-18. Everything we've looked at so far, RSGC 1-F01 pushing up against the theoretical size ceiling, VY Canis Majoris swallowing the space between the Sun and Jupiter, all of it gets surpassed by a star that most people have never heard of. Stephenson 2-18 is, by current measurements, the largest known star in the universe, and the numbers attached to it are genuinely difficult to process. The star sits about 18,900 light-years away, also in the constellation Scutum, the same region of the inner galaxy that keeps producing these monsters. It was discovered by American astronomer Charles Bruce Stephenson, who identified it through infrared survey data. That detail matters. Stephenson 2-18 isn't something you can find by pointing a regular optical telescope at the sky. This part of the galaxy is heavily obscured by dust, and the only way to see through that dust is to look in infrared wavelengths where the obscuration is weaker. Stephenson was working through that data when he cataloged the cluster now bearing his name, Stephenson 2, a dense open cluster packed with red supergiants. And the star we now call Stephenson 2-18 was initially not even considered a member of the cluster. It sat off to the side, not obviously associated with the group. Later analysis revised that conclusion. It wasn't an unrelated background star. It was part of the cluster, and it was enormous. The vital statistics are almost numbing at this point, but they're worth going through carefully. Stephenson 218 has a radius of approximately 2,150 solar radii. Its surface temperature sits around 3,200 Kelvin. Spectral type M6, deep red, cooler than most campfires. And despite that low surface temperature, it shines at roughly 436,000 times the luminosity of our Sun. That's what happens when a star is so vast that even a cool surface temperature radiates an almost incomprehensible amount of total energy. The surface area alone is doing the work. Now, the solar system comparison. At 2,150 solar radii, if you removed our Sun and replaced it with Stephenson 218, centered exactly where our Sun sits today, where would the surface of this star be? This is the question that should stop you cold. Mercury? Gone. Venus? Gone. Earth? Gone. Mars? Gone. The entire asteroid belt? Gone. Jupiter, the largest planet in our solar system, a gas giant 11 times the diameter of Earth? Gone. Saturn, the planet with the rings, orbiting nearly 900 million miles from the Sun. The surface of Stephenson 218 would reach past Saturn's orbit. Everything inside Saturn's path around the Sun would be submerged inside this star, not orbiting near its surface, not skimming through its outer atmosphere, buried inside it. You're talking about 6 planets, the asteroid belt, and billions of miles of what we think of as empty space, all swallowed by a single star. Uranus and Neptune, the 2 outermost planets, would survive, orbiting outside the star's photosphere. But the rest of the solar system as we know it would simply not exist. Think about that for a second. Every place humans have ever sent a spacecraft, the Moon, Mars, Jupiter's moons, Saturn's rings, all of that would be inside this star. The Voyager probes, launched in 1977 and now billions of miles from Earth, would still be traveling through the interior of Stephenson 2-18. The star is not just large by astronomical standards, it is large by solar system standards. Now we need to think about what this means for the physics. Earlier in this video, we talked about the Hayashi limit, the theoretical upper boundary on stellar radius, sitting at around 1,500 solar radii. The argument is straightforward. Beyond that size, a star becomes physically unstable. Radiation pressure from the core outpaces gravity's ability to hold the outer layers together. The star should lose mass faster than it can maintain its radius. It simply shouldn't be able to stay that big. Stephenson 2-18 is measured at 2,150 solar radii. That's not close to the limit. That's not nudging up against it. That's 650 solar radii past the theoretical ceiling, more than 40% beyond where physics says a star should be able to exist. And this is where things get genuinely uncomfortable, because there are really only a few ways to interpret that. One possibility is that the measurements are wrong. Stephenson 2-18 is nearly 19,000 light-years away, deeply embedded in a dusty region of the galaxy. The same factors that make these stars hard to measure, distance uncertainty, dust extinction, the difficulty of directly resolving a stellar disk at that range, could be inflating the size estimate. If the distance is slightly off, the radius calculation shifts accordingly. This has happened before. UY Scuti was measured at 1,708 solar radii. Revised data brought it down to about 775. A similar correction for Stephenson 2-18 wouldn't be unprecedented. But here's the other possibility. Maybe the measurements are basically right and our theoretical models are incomplete. The Hayashi limit is derived from stellar physics models that make certain assumptions about how stars behave at extreme sizes. Assumptions about opacity, convective energy transport, mass loss rates, and the interplay between radiation pressure and gravity. If some of those assumptions break down at the very upper end of the size distribution, the limit might not be as hard a ceiling as we think. Stars at the edge of stability might temporarily exceed it through pulsation cycles. Mass loss rates might be variable in ways that allow brief periods of extreme expansion. The models might be missing something, or, and this is the genuinely unsettling option, both things are partially true. The measurements carry real uncertainty, and the theory is also incomplete, and the actual size of Stephenson 218 sits somewhere in the gap between what we can precisely observe and what we can confidently predict. What's not in doubt is that this star is extraordinary. Even a radius of 1,800 solar radii, a significant downward revision from the current best estimate, would make it one of the largest objects ever observed. At the current figure of 2,150 solar radii, it sits in a category essentially alone. No other star we've measured comes close. RSGC 1-F01 at around 1,530 solar radii. VY Canis Majoris at roughly 1,400. Those are enormous stars. Stephenson 2-18 is in a different conversation. The star is an M6-type red supergiant, which means it has already passed through the main phases of its stellar life. The hydrogen burning that defined its early existence is long over. It has expanded outward into this almost incomprehensible size as its core conditions have changed. At some point, and the timeline is deeply uncertain, it will either shed enough mass to collapse inward, or its core will reach the point where iron accumulates and fusion stops producing energy. When that happens, the result will be violent. A core collapse supernova, a neutron star or black hole remnant, and a shockwave of energy expanding outward into the surrounding cluster. But we don't know when. We don't know precisely how big it is. We don't know whether our models of stellar physics at these scales are accurate enough to trust. And the fact that we don't know which of those is true tells you something important about how much we still have to learn. Everything we've talked about so far has been within our own galaxy. Every star on this list, Betelgeuse, VY Canis Majoris, RSG C1-F01, Stephenson 2-18, sits inside the Milky Way. They're distant, yes. Some of them are nearly 19,000 light-years away. But they're ours. They're part of the same galaxy we live in. WOHG 64 is something different entirely. WOHG 64 sits in the Large Magellanic Cloud. That's a dwarf galaxy orbiting the Milky Way at a distance of roughly 160,000 light-years. Not 9,500 light-years like UY Scuti. Not 18,900 light-years like Stephenson 2-18, 160,000 light-years. The light you'd be seeing from WOHG 64 tonight left that star around the time early modern humans were spreading across the African continent. That's how far away this object is. And yet in 2024, astronomers captured a direct close-up image of it. The first time in history that a star outside our galaxy had ever been imaged in that kind of detail. That alone would make WOHG 64 worth talking about. But the image is almost the least interesting thing about this star. WOHG 64 was first identified back in the 1970s as a star of unusual interest within the Large Magellanic Cloud. Subsequent observations revealed it wasn't just unusual, it was enormous. Early estimates put its radius at more than 1,500 solar radii. That places it in the same extreme tier as the largest stars in our own galaxy, potentially rivaling Stephenson 2-18 at the very top of the size rankings. For decades, it was classified as a red supergiant, massive and cool, the kind of star that fits the pattern we've already established in this video. Large, red, dying, surrounded by material it had shed into space over thousands of years. Everything about it looked familiar, if you can call a star 160,000 light-years away familiar. Then things got complicated. In 2024, researchers studying more than 30 years of brightness data noticed something that didn't fit. WOHG 64 had gotten hotter, not by a small amount. The surface temperature had climbed by over 1,000 degrees Celsius. The star, which had been glowing red, was now appearing yellow. That's not a trivial shift. Red and yellow correspond to completely different stellar classifications. A yellow hypergiant is a fundamentally different kind of object than a red supergiant, hotter, more compact, in a different phase of evolution. Based on these new observations, some researchers proposed that WOHG 64 had transitioned into a yellow hypergiant, and if that reclassification was correct, the star's radius dropped dramatically, down to around 800 solar radii. Still a genuinely enormous star, but not 1,500, not a record contender. Something different. That's a remarkable revision, and it matters because it changes what we think is happening to this star. A red supergiant nearing death behaves one way. A yellow hypergiant nearing death behaves another way. These aren't minor distinctions. They represent different positions on the evolutionary track, different timescales, different fates. Then, in early 2026, a new team published spectroscopic data that complicated things again. The molecular absorption signatures in WOHG64's spectrum, the kind of fingerprints that reveal what a star's atmosphere is actually made of and how hot it is, appeared to indicate the star was still a red supergiant after all, still cool, still expanded, still fitting the original classification. The 2024 reclassification, according to this newer analysis, may have been premature. So right now, we genuinely don't know what WOHG 64 is. That's not a comfortable place to be, but it's an honest one. What everyone agrees on is the behavior, and the behavior is extraordinary. The star dimmed significantly around 2011, then it reheated and brightened. Then it faded again in 2025. These aren't small fluctuations. Variable stars brighten and dim all the time. Betelgeuse does it, and so do most red supergiants to some degree. But these swings in WOHG 64 are dramatic, and they're happening on human timescales. A star this size changing this much this quickly is not something astronomers have a clear precedent for. Most of what we know about stellar evolution comes from studying many different stars at different points in their lives and piecing together a timeline. We don't usually get to watch a single star this massive change in real time. What's likely happening at some level is mass loss. Red supergiants and hypergiants in the late stages of their lives shed enormous amounts of material. The outer layers become unstable. The star essentially throws pieces of itself into space. That ejected material forms a thick surrounding nebula of gas and dust. And WOHG 64 is known to have exactly that. A dense envelope of circumstellar material that makes precise measurements even harder, because you're trying to see through a cloud that the star itself produced. When a star ejects a large mass of hot plasma that then cools into dust, you get dramatic dimming. That's what happened to Betelgeuse in 2019. The same mechanism is almost certainly at work in WOHG 64, possibly at a far larger scale. This kind of behavior is what the end of a massive star's life actually looks like. Not a clean, orderly shutdown. something violent and unpredictable. The star is no longer in equilibrium. The forces holding it together and the forces trying to blow it apart are no longer balanced, and the result is instability that propagates outward in ways that are difficult to model and harder to predict. Mass loss accelerates. The star's luminosity fluctuates. Its apparent color changes as the temperature shifts, and the surrounding dust scatters light differently. From 160,000 light-years away, that chaos shows up as the kind of dramatic brightness swings we've been recording in WOHG 64 for the past 15 years. The 2024 image changes something important about all of this. For the first time, astronomers weren't just measuring WOHG 64 indirectly through brightness curves and spectral data. They were actually looking at it. The image showed a clearly elongated asymmetric structure, not a perfect sphere, but a star already distorted by the mass it's shedding, surrounded by the dusty torus of material it has expelled. That's the face of a dying giant, caught in the act. Whether WOHG 64 ultimately gets reclassified as a yellow hypergiant or confirmed as a red supergiant, whether its true radius is 800 solar radii or 1,500, whether it's days or millennia from a supernova event, none of those questions have clean answers yet. What we have instead is a star that is actively changing in a galaxy beyond our own, close enough to image and far enough that the light we're seeing left it 160,000 years ago. Whatever WOHG 64 is doing, it's doing it right now, and we're watching in real time. There's something that needs to be said here because it trips up almost everyone who looks into this topic. Everything we've covered so far has been about physical size, volume, how much space a star takes up, and the stars at the top of that list, Stephenson 2-18, WOHG 64, VY Canis Majoris, are red supergiants and hypergiants, enormous, bloated, cool, and dim relative to their size. But size is not the same thing as mass. And when you start asking which stars contain the most actual matter, the leaderboard looks completely different. Think about what mass and volume actually mean. Mass is how much material a star contains, how many atoms, how much hydrogen and helium packed together by gravity. Volume is simply how much space the star occupies. These two things can be wildly different. A red supergiant like Stephenson 2-18 has expanded to fill an almost incomprehensible amount of space, but its outer layers are extraordinarily thin. The density of gas at the photosphere of a red supergiant is far lower than the best laboratory vacuum we can produce on Earth. There's almost nothing there. The star is vast but diffuse. Most of its mass is still packed into the relatively small core region buried deep inside. Now consider R136A1. R136A1 sits in the Tarantula Nebula, a massive star-forming region in the Large Magellanic Cloud, about 160,000 light-years away. It's the same dwarf galaxy we mentioned when discussing WOHG 64. Estimates put R136A1 at somewhere between 170 and over 200 solar masses. That's 170 to 200 times the mass of our entire Sun crammed into a single stellar object. No red supergiant comes close to that number. Stephenson 2-18, for all its staggering volume, contains somewhere in the range of 12 to 15 solar masses. R136A1 contains more than 10 times as much actual matter. But here's the thing. R136A1 is not particularly large by the standards of what we've been discussing. It's a blue hypergiant, extremely hot with surface temperatures around 46,000 Kelvin. Compare that to Stephenson 2-18's surface temperature of roughly 3,200 Kelvin. R13601 is burning at over 14 times the surface temperature of the current record holder for volume, and its radius, roughly 30 to 40 solar radii. That's not small by any normal measure, but placed next to Stephenson 218 at 2,150 solar radii, it's essentially a point. So how is it possible that a star with over 10 times the mass ends up so much more compact? The answer is in where R136A1 is in its life cycle. R136A1 is still in the main sequence, or close to it. It's still burning hydrogen in its core. Massive stars like this are dense, extraordinarily hot, and intensely luminous. They burn through fuel at a rate that's almost violent. R13601 is roughly 1,000,000 times more luminous than our Sun. It's one of the brightest individual stars known to exist, but it hasn't yet entered the phase that would cause it to expand outward. It hasn't evolved off the main sequence and ballooned into a red supergiant. That expansion only happens later, when the hydrogen in the core runs out and the star's outer layers begin to move outward as the internal structure changes. That's when volume increases dramatically. That's when you get the enormous, cool, diffuse objects we've been talking about all night. R13601 is still in the earlier, more compressed stage, all that mass, still packed relatively tight. And there's a genuinely unsettling possibility for stars like R136A1. They may never become red supergiants at all. Stars above a certain mass threshold, somewhere around 40 solar masses, follow a different path at the end of their lives. The radiation pressure from their own luminosity is so intense that it constantly drives material off the stellar surface, eroding the star's outer layers throughout its life. By the time a truly massive star runs out of fuel, it may have shed so much of its mass through stellar winds that the path toward red supergiant expansion is simply cut off. Instead, these stars may evolve toward different endpoints entirely. Some are thought to end in pair instability supernovae, explosions so energetic that there's nothing left, no neutron star, no black hole, just an expanding cloud of material scattered through space. Others may collapse directly into black holes without a visible explosion at all. The most extreme stars don't get to be big and puffy. They burn too hard, too fast, and too bright. They're gone before they ever get a chance to swell into something like Stephenson 218. This creates a real paradox when you try to identify the most extreme star in the universe. It depends entirely on what you mean by extreme. If you want sheer volume, you're looking at red supergiants and hypergiants, objects so expanded that our entire solar system out to Saturn's orbit would fit inside them. If you want raw mass, you're looking at blue hypergiants and Wolf-Rayet stars, dense and ferociously energetic objects that would barely register on the size charts we've been discussing. If you want luminosity, raw energy output, again, the blue hypergiants and Wolf-Rayet stars dominate, some of them pouring out energy at millions of times the solar rate. If you want the most powerful magnetic fields, the most intense radiation, the most extreme endpoints, you're looking at something else again. The universe doesn't have a single answer to the question of what's most extreme. It has many different categories of extreme, and they don't overlap cleanly. So when we say Stephenson 218 is the largest known star, what we mean is it occupies more volume than anything else we've found, which is not the same thing as saying it's the most powerful or the most extreme. Numbers can only take you so far. At some point, the figures stop landing. 2,150 solar radii, 436,000 times the luminosity of our Sun. These are real numbers, carefully measured, and they mean almost nothing to a human brain that evolved to track prey across a savanna. So let's try something different. Let's try to actually go there. Imagine you're somehow positioned at the photosphere of Stephenson 2-18. The first thing to understand is that the word surface is almost meaningless here. There is no ground beneath you. There is no defined boundary where the star ends and space begins. What you'd be floating in is an extraordinarily thin gas, plasma technically, so diffuse that it makes the best vacuum ever produced in an Earth laboratory look dense by comparison. The photosphere of a red supergiant has a density roughly 1 billion times lower than the air you're breathing right now. You wouldn't feel it against your skin. You would pass through it without resistance. And yet this emptiness is glowing, radiating energy at around 3,200 Kelvin, cooler than our sun's surface, but hot enough to fill everything around you with a deep, reddish-orange light. Not the sharp white glare of something like the sun. Something more diffuse, more ancient feeling, if that makes any sense. The light comes from everywhere at once, because in every direction you look, more star continues. The horizon, if you can even call it that, curves away from you impossibly slowly. Because the star is so vast, the curvature is nearly imperceptible. It looks in every direction like a flat ocean of dim fire stretching to the edge of your vision. The gravity here surprises people. You'd expect standing at the surface of a star to feel crushingly intense, but it doesn't work that way. Gravity depends on how close you are to the concentrated mass, and in a star this expanded, the photosphere is an enormous distance from the dense core where nearly all the mass actually lives. At the surface of Stephenson 2-18, the effective surface gravity is a small fraction of what you'd feel on Earth. You'd float there, nearly weightless, in that tenuous glowing gas. Beneath you, if below means anything, the interior is not quiet. Red supergiants are violently convective. The outer layers are churned by enormous convection cells, columns of hot plasma rising from the deep interior and cooler material sinking back down. These convection cells are not small. In a star like Stephenson 2-18, individual convection cells can be comparable in size to our entire solar system, not our inner solar system. The whole thing, out to the far reaches, encompassed in a single rising column of plasma. This churning is continuous and slow by human standards, but the energies involved are incomprehensible. Material is constantly cycling, up, across, down, carrying heat from the interior toward the surface in enormous lazy loops. We don't have to purely imagine this. Betelgeuse, much closer to Earth than Stephenson 2-18, has actually been resolved well enough that astronomers have imaged features on its surface directly. What they found were bright spots, hot, elevated regions corresponding to the tops of those giant convection cells, where hotter material has risen from below and is now radiating into space. The Great Dimming of 2019 was tied to exactly this kind of activity. A mass ejection from one of these convection events threw material outward, which cooled into dust and temporarily blocked a portion of the star's light. These are not calm objects. They boil. Now pull back. Move far enough away to orbit this thing. Say, at the distance Mercury orbits our sun. On that imaginary planet, close enough to feel the warmth, what does the sky look like? The star doesn't look like a sun. It doesn't look like a point of light or even a disk the way our sun appears from Earth. It fills the sky. Not all of it, but a staggering, disorienting fraction of it. Deep red, not white. Its edges are not crisp. The photosphere bleeds outward into a hazy atmospheric limb, so the star seems to fade at its margins rather than end cleanly. You'd see texture, actual texture on the surface, bright patches where convection cells push hotter material upward, darker regions where cooler gas has descended. The surface moves, not quickly by human standards, but visibly, over weeks and months. The star seethes. At closer orbits, the situation gets even stranger. The radiation pressure from a star this luminous, 436,000 times the Sun, would be intense enough to affect the orbit of anything nearby. The stellar wind streaming outward from the photosphere is not a gentle flow the way our Sun's solar wind is. It's a gale. Red supergiants in the final stages of their lives shed enormous amounts of mass this way, blowing their outer layers into the surrounding space and building up an expanding nebula of cast-off material. If you were orbiting Stephenson 218 at close range, you'd be inside that outflowing gas. The space around you would not be the clean vacuum of our solar system. It would be filled with dust and molecules and slowly expanding shells of the star's own former atmosphere. The sky during a sunset on a planet at moderate distance would be extraordinary and deeply unsettling. As the star drops toward the horizon, the light reddens further. Already red to begin with, it shifts into something almost infrared. The shadows it casts are long and soft-edged because the star subtends too large an angle to produce sharp shadows. Everything is bathed in a dim, warm, reddish glow that doesn't really disappear even when the star is partially below the horizon, because the atmosphere catches and scatters that red light in every direction. That's what it means to orbit a red supergiant, not the cold pinpoint of light we see from Earth, but a sky half filled with something ancient and dying and impossibly vast. Every one of these stars is dying. Not slowly, not peacefully, in the way that a star the size of Stephenson 218 or VY Canis Majoris dies. There is nothing quiet about it. These objects have been burning through their fuel at a rate so extreme that what took our Sun billions of years to do, they accomplish in a few million. And when the fuel runs out, the consequences are almost impossible to overstate. Here's how it works. A red supergiant spends most of its life fusing hydrogen into helium in its core. When the hydrogen is gone, the core contracts and heats up enough to start fusing helium. When the helium runs out, carbon burning begins. Then neon. Then oxygen. Then silicon. Each stage releases less energy than the one before it and lasts for a shorter period of time. The silicon burning phase, which produces iron, lasts only a few days. And then comes the problem. Iron is the end of the road. Fusing iron doesn't release energy, it absorbs it. The moment an iron core builds up at the center of a massive star, the engine stops. There's nothing left to generate the outward pressure that has been holding the star up against its own gravity for millions of years. The core, which by this point is roughly the mass of the Sun compressed into a sphere roughly the size of a city, collapses in less than a second. Less than a second. A structure larger than Earth reduced to something 20 kilometers across in the time it takes you to blink. What happens next is one of the most violent events in the universe. The collapsing core compresses until the neutrons themselves resist further compression, and the infalling outer layers of the star slam into that rigid surface and rebound. The resulting shock wave tears outward through the star at tens of thousands of kilometers per second. The outer layers, the enormous bloated envelope of gas that gave these stars their staggering size, are blasted into space. This is a core collapse supernova. The energy involved is genuinely difficult to frame. In those first few seconds, the explosion releases more energy than our Sun will emit across its entire 10 billion year lifetime. Most of that energy comes out as neutrinos, nearly massless particles that pass through ordinary matter almost without interacting. The visible light and heat that we'd actually observe from Earth is only a tiny fraction of the total energy. And yet that small fraction is enough to briefly outshine entire galaxies. What's left behind depends on how massive the original star was. In most cases, the compressed core survives as a neutron star, an object roughly 1.4 times the mass of the Sun, packed into a sphere about 20 kilometers across, spinning rapidly and radiating enormous energy. The density of a neutron star is so extreme that a single teaspoon of its material would weigh about 1 billion tons on Earth. Betelgeuse, at around 15 solar masses, is expected to leave behind a neutron star when it finally goes. The outer layers will be gone, scattered across light years of space. What remains will be this tiny, spinning remnant where one of the largest stars visible to the human eye once burned. For more massive progenitors, the red hypergiants like VY Canis Majoris, stars that began their lives with dozens of solar masses, the outcome may be different. If the collapsing core is massive enough, even neutron degeneracy pressure can't stop the collapse. The core keeps contracting until nothing can halt it, and a black hole forms. The outer layers may still be expelled in an explosion, or they may simply fall inward with the core. In some cases, there may be no visible supernova at all. That last possibility is something astronomers have started to take seriously. It's called a failed supernova. A massive star, instead of exploding spectacularly, simply disappears. One year it's there, the next it's gone, with no bright flash, no expanding nebula, no visible signal of what happened. Researchers have identified a small number of candidate cases, stars that were cataloged and then were simply no longer present in follow-up observations. The leading explanation is that the core collapsed directly into a black hole without triggering the outward shock wave that would produce a visible explosion. The star doesn't explode, it vanishes. For the most massive stars in the universe, that may be the most common ending. Now think about what Betelgeuse's supernova will actually look like from here. Betelgeuse is roughly 548 light-years away. When it goes, and it will go within the next 100,000 years, possibly much sooner, the light from that explosion will reach Earth and it will be extraordinary. At its peak brightness, the supernova will be visible in full daylight. At night, it will cast shadows. It will be brighter than the full moon. It will remain visible to the naked eye for weeks, possibly months, slowly fading as the expanding cloud of debris cools and spreads. The last time a supernova was visible to the naked eye from Earth was SN 1987A, which exploded in the Large Magellanic Cloud about 168,000 light-years away. That one was barely visible without a telescope. Betelgeuse is 300 times closer. The show will be incomparably more dramatic. And after it fades, Orion will look different. One of the stars that has defined that constellation for as long as humans have been looking up will simply be gone. In its place, for a time, there will be a faint nebula, the glowing remnant of what was once a star, large enough to swallow our entire inner solar system. What's remarkable is what those explosions leave behind in a broader sense. When a red supergiant goes supernova, the shockwave doesn't just destroy, it creates. The extreme temperatures and densities in the explosion synthesize heavy elements that couldn't be produced by ordinary stellar fusion. Gold, platinum, uranium. These elements form in the final seconds of the explosion and are flung outward into the surrounding interstellar medium. Over millions of years, that material drifts through the galaxy, eventually mixing with gas clouds, eventually collapsing into new stars and new planetary systems. The iron in your blood was forged in a stellar core. The calcium in your bones came from a star that died before our sun was born. The oxygen you're breathing right now was scattered across space by an explosion that happened billions of years ago in a star that no longer exists. We are not observers of this process from a safe distance. We are the product of it. The atoms in your body were forged inside stars like these and scattered across the galaxy by their deaths, which means, in a very real sense, you're made of the remains of something that was once the largest star in its neighborhood. Stephenson 218 sits at the top of the list right now, but there's a question that hangs over all of this. Is it actually the largest star in the universe? Or is it just the largest star we've managed to find so far? Those are very different questions, and the answer matters more than it might seem. The Milky Way contains somewhere between 200 and 400 billion stars. That range alone should give you pause. We can't even count our own galaxy stars precisely enough to narrow it down better than that. Of those hundreds of billions of stars, we have detailed size measurements for a tiny fraction. We're talking about a few thousand stars with well-characterized radii, out of a population that could exceed 400 billion. The coverage is, to put it plainly, almost non-existent. And the stars we haven't measured aren't randomly distributed. The inner regions of the Milky Way, the galactic center, the densely packed bulge, are buried behind enormous columns of interstellar dust. Visible light doesn't penetrate that dust. Infrared light does, which is why the stars we've been discussing tonight, Stephenson 2-18, RSGC 1-F01, and the rest, were found through infrared surveys rather than traditional optical telescopes. Those surveys are powerful, but they haven't mapped everything. There are regions of the inner galaxy where the dust is thick enough that even infrared observations become unreliable. We don't know what's hiding in those regions. We genuinely don't. So the honest answer to whether Stephenson 2-18 is the largest star in the Milky Way is, we have no idea. It's the largest one we've confirmed. That's not the same thing. Now extend that logic outward. The observable universe contains somewhere around 2 trillion galaxies. Each of those galaxies contains hundreds of billions of stars on average. The total number of stars in the observable universe is estimated at something like a septillion. That's a 1 followed by 24 zeros. Stephenson 2-18 at 2,150 solar radii is an extreme outlier even by the standards of our own galaxy. But across a septillion stars, extreme outliers become almost statistically inevitable. The question isn't really whether a larger star exists somewhere in the universe. It almost certainly does. The question is whether we'll ever be able to find it. That's where the problem gets genuinely grim. Measuring the radius of a star like Stephenson 2-18 is already difficult, and it's only 18,900 light-years away. Now try to do that same measurement for a star in a galaxy 10 million light-years away, or 100 million. The angular sizes become so small that even our best instruments, stellar interferometers, the James Webb Space Telescope, can't resolve individual stars in most cases. There are exceptions. Nearby galaxies like the Large Magellanic Cloud are close enough that we can image individual stars, which is exactly how WOHG 64 was found and studied. But the further you go, the more individual stars blur into the general glow of their host galaxy. If the actual largest star in the universe is sitting in a galaxy a billion light-years away, we will probably never know it exists. Tort. Then there's the theoretical question, which is its own puzzle. The Hayashi limit sets a theoretical ceiling on stellar radius at around 1,500 solar radii. The physics behind it is real. As a star expands and its luminosity increases, Radiation pressure from the interior eventually exceeds the inward pull of gravity, and the star's outer layers should be blown away before the radius can grow further. The theory predicts that stars simply cannot maintain structural stability much beyond that limit, and yet Stephenson 2-18 appears to have a radius of 2,150 solar radii. That's 600 solar radii beyond where theory says it should stop. There are a few ways to interpret that. One possibility is that the measurement is wrong. As we covered earlier, distance uncertainty compounds every size estimate, and Stephenson 218 is nearly 19,000 light-years away. A meaningful error in the distance estimate would change everything. The measurements are better now than they used to be, but they're not perfect. Another possibility is that the Hayashi limit isn't a hard wall. Some researchers have proposed that stellar pulsation, the kind of rhythmic swelling and contracting we see in variable stars, might allow a star to temporarily exceed the theoretical maximum radius. If a star is caught mid-pulse at its most expanded point, a snapshot measurement could record a radius that wouldn't be sustained over time. It wouldn't be a stable size, just a momentary extreme. Mass loss rates complicate the picture further. Red supergiants shed enormous amounts of material into space as they near the end of their lives. That outflow of mass changes the star's structure in ways that are difficult to model precisely. Magnetic fields may play a role too, potentially supporting the outer layers against radiation pressure in ways that standard models don't fully account for. None of these explanations are settled. Scientists are still working through them. What's striking about all of this is how much uncertainty sits at the very top of the list. The star we currently believe to be the largest known in the universe may be smaller than we think, and may be violating physical laws that we believed were well established. Both of those things might be true simultaneously. That's not a comfortable position to be in, but it's an honest one. The history of this particular question, which star is the largest, is a history of records being broken and measurements being revised. UY Scuti lost its title when better data arrived. WOHG 64's classification is still being contested in real time. The leaderboard has changed repeatedly in just the past decade, and there's no reason to think it won't change again. The next major infrared survey, the next generation of interferometers, the next careful distance measurement could move Stephenson 2-18 down the list or push it further ahead. We've been staring at the sky for thousands of years, and we're still finding things we never expected. Start with light. You already know light is fast, about 186,000 miles per second, the fastest thing in the universe. When light leaves the surface of our sun, it takes roughly 4.6 seconds to cross the sun's full diameter from one side to the other. That's less time than it takes to tie your shoes. Now apply that same speed to Stephenson 218. Light, traveling at 186,000 miles per second, would take more than 4 hours to cross that star from edge to edge. 4 hours. You could board a flight from New York to Los Angeles, land, collect your luggage, and drive to your hotel. And light would still be crossing Stephenson 2-18. That's what 2,150 solar radii actually means when you run it against something real. Now try sound. Sound can't travel through the vacuum of space, but humor the thought experiment. If you were standing on the surface of Stephenson 218 and fired a cannon aimed at the opposite side of the star, and if the sound wave could somehow propagate through those thin, superheated outer layers, it would take over 800 years to arrive. Not 800 seconds, not 800 minutes, 800 years. The cannon fires in the year 2025. The sound reaches the other side sometime after the year 2800. Everyone who ever lived when that cannon fired is gone. Their children are gone. Their children's children are gone. And the sound is still traveling. Volume is where the numbers become genuinely grotesque. Stephenson 2-18 could contain roughly 10 billion of our suns packed inside it. 10 billion. The sun itself could swallow 1.3 million Earths. So you're looking at a star that could hold, by rough calculation, something on the order of 13 billion trillion Earths. That figure doesn't mean anything to a human brain. It can't. We didn't evolve to process numbers like that, but the fact that the number is so far beyond comprehension is itself the point. Try the scale model. Shrink Stephenson 2-18 down to the size of a basketball, a standard NBA basketball about 9.4 inches across. At that same scale, our sun would be smaller than a grain of sand. Not a marble, not a pea. A grain of sand. And the Earth at that same scale would be a microscopic speck, invisible to the naked eye, floating somewhere in the room. If you held that basketball and looked at the grain of sand next to it, you would be looking at the actual proportional relationship between the largest known star and the star that lights our entire solar system. Consider also what this relationship means in practice. If Stephenson 2-18 replaced our sun and occupied the same orbit, the grain of sand, our actual sun, would become utterly insignificant. The massive red star would dominate the sky so completely that all other light sources would fade from perception. The comparison stops being theoretical and becomes visceral. Now flip the perspective entirely because the numbers are only half of it. Imagine you're somehow hovering at the photosphere of Stephenson 2-18, the outermost layer that astronomers treat as the star's surface. Look down. You'd see nothing useful. The interior is opaque, seething plasma, hot gas layered upon hotter gas, all of it blending downward into temperatures and pressures that no instrument we've built could survive. There's no hard surface, there's no ground. There's just a gradual thickening of gas that eventually becomes something you could call the star's body, though the boundary is more suggestion than fact. Now look up. The star curves away from you in every direction. Not the gentle curve of Earth's horizon you might see from a high-altitude aircraft, a curve so vast and slow that it almost seems flat at first. From the photosphere of Stephenson 2-18, the horizon would be unimaginably distant. The star's surface would stretch away from you for hundreds of millions of miles before curving out of sight. Look left, look right, look behind you. The same surface rolling away into a red-lit infinity. You are not standing on something small. You are standing on something so large that your location on it is essentially meaningless. The star doesn't notice you. It can't. Think about the travel time on that surface. If you could somehow drive across the surface of Stephenson 2-18 at highway speed, 65 miles per hour, windows down, the journey would take roughly 3 million years. That's longer than modern humans have existed as a species. You'd set out driving before Homo sapiens appeared on Earth, and you still wouldn't have finished the trip by today. One more comparison. Light from our sun takes about 8 minutes to reach Earth. At 2,150 solar radii, the near edge of Stephenson 2-18, if it sat where our sun sits, would already be past Earth's orbit. The far edge would be past Saturn. If you were standing on what we call Earth's orbit and trying to look at the star, you wouldn't see a star in the sky. You'd be inside the star. You'd be surrounded by it. There would be no sky. There would be no view. There would just be the star in every direction and temperatures that would vaporize anything we've ever built in milliseconds. The star wouldn't acknowledge your existence. It's simply too vast, too consumed with its own internal processes to register something as small as a human being. None of these comparisons fully work, and that's kind of the point. There's something worth asking, which is why we care so much about which star is the biggest. It's not an obvious question to care about. Knowing the answer doesn't change anything practical. It won't affect your commute or your electricity bill. And yet, videos about the largest stars in the universe pull millions of views. The question appears on astronomy forums constantly. It's one of the most searched topics in all of space science. There has to be a reason for that. The reason probably goes back a long way. Humans evolved in an environment where mapping your surroundings was survival. You needed to know where the largest predator was, how fast it could move, whether it was the biggest threat in the area. That instinct didn't disappear when we built cities and started looking at telescopes. It just redirected. We still want to find the largest thing, the fastest thing, the most extreme thing. We just scaled the search up from the savannah to the observable universe. Cosmic record-breaking is the same ancient drive operating at a scale our ancestors couldn't have imagined. When you watch a video about the biggest star ever found, some part of your brain is doing exactly what brains evolved to do. Cataloging threats and extremes, mapping the boundaries of the environment. The environment is just a lot bigger now, and there's something specifically compelling about stars. They sit at the edge of comprehension. You can look up on any clear night and see them, these tiny fixed points of light, and know intellectually that each one is a nuclear furnace millions of kilometers across. That gap between what your eyes report and what your mind knows creates a kind of tension. Finding out which one is the biggest doesn't resolve that tension. It deepens it. The answer is always more disorienting than you expected, and that disorientation is part of the appeal. What's interesting is how much the answer has changed even recently. 10 years ago, the standard answer to this question was UY Scuti. That was the star in the videos, the infographics, the school presentations. It was measured at roughly 1,700 solar radii and was treated as a settled fact. Then better distance data arrived and the radius was revised down to around 775 solar radii. Less than half. A star that had held the record in the public imagination for years turned out to be nowhere near as large as everyone thought. And now Stephenson 218 sits at the top of the list at approximately 2,150 solar radii. A star that wasn't even widely discussed a decade ago. The record holder changed completely, and it may change again. That's an uncomfortable thing to sit with if you expect science to deliver permanent answers. But that discomfort is worth examining. What the UY Scuti revision actually showed was that the measurement tools got better. The Gaia Space Telescope produced more precise distance measurements than anything that came before it, and those better measurements corrected an error. That's not science failing. That's science doing exactly what it's designed to do. The previous answer was the best available answer at the time. The new answer is better, and the next answer may be better still. WOHG 64 is another example of this. Researchers spent decades studying that star, measured it at over 1,500 solar radii. Then in 2024, observed changes that led some of them to reclassify it as a yellow hypergiant at only around 800 solar radii. Then, in early 2026, new spectroscopic data pushed back against that reclassification, suggesting the star is still a red supergiant after all. The record on that star is genuinely unsettled right now. If you want a clean, confident answer about WOHG 64's size, you're not going to get one. What you get instead is a picture of researchers actively arguing, gathering new data, revising their models. That's uncomfortable. It's also the only honest account of where the science stands. Most people want knowledge delivered as certainty. That's understandable. Certainty is easier to remember and easier to share. But scientific knowledge isn't certainty. It's the best current answer, held with appropriate confidence and subject to revision. The stars at the top of the size list represent that reality better than almost any other example in astronomy. The measurements are hard, the distances are enormous, the instruments have limits, and so the rankings shift. What doesn't shift is the underlying drive to find the answer. Every time a new survey reveals a previously uncatalogued red supergiant buried in the inner galaxy behind layers of dust, astronomers measure it. Every time a larger telescope comes online, someone points it at the known giants to refine the numbers. The search is genuinely ongoing. The inner regions of the Milky Way are still only partially mapped in the wavelengths that can pierce that obscuration. It's entirely possible, some would say likely, that there are red supergiants out there larger than Stephenson 218 that no one has measured yet. The largest known star and the largest existing star may not be the same object. That possibility is part of what makes this question so persistent. Every time you find the biggest thing, you're also finding the current edge of what you can see. The search for the largest star is really a search for the limits of observation, which is a search for the limits of knowledge itself. You want to know what's out there. You want to know where the extremes are. You want the map to be complete. It never quite is. But the answer keeps changing. And that's not a bug. That's exactly how it's supposed to work. So let's put all of this together. We've covered a lot of ground tonight, and it helps to line everything up side by side so you can actually see what we're dealing with. Think of it as a ladder. Each rung takes you somewhere that the one below it couldn't prepare you for. At the bottom of that ladder is our sun, one solar radius, about 865,000 miles across. It takes light roughly 4.6 seconds to cross its diameter. For most of human history, the sun was simply the largest thing anyone could conceive of. It is 1.3 million times the volume of Earth. And by the end of this list, it will seem almost microscopic. Next comes Betelgeuse. You can find it tonight if you step outside and look at Orion. That reddish star marking his right shoulder, that's a red supergiant roughly 764 times the radius of our sun, variable enough that it pulses between around 550 and 920 solar radii as it expands and contracts. If you dropped it at the center of our solar system, it would swallow Mercury, Venus, Earth, and Mars, and push its surface toward Jupiter's orbit. It's about 548 light-years away, which makes it practically next door by the standards of everything else on this list. It's also dying, not on a human timescale, but in astronomical terms. It's close. When it goes supernova, every person on Earth will be able to see it in full daylight. Betelgeuse matters because it's the giant you can actually see with your own eyes right now on any clear night. Then there's VY Canis Majoris, roughly 1,400 solar radii, about 3,900 light-years away in the constellation Canis Major. At that size, we're talking about a sphere roughly 2 billion kilometers across. More than 5 billion suns could fit inside it by volume. VY Canis Majoris isn't just large, it's violently unstable. shedding enormous amounts of mass into the surrounding space and wrapping itself in nebulosity. It's a hypergiant, a classification reserved for stars so extreme they've pushed beyond the supergiant category into something harder to define. The numbers at this point start to feel almost arbitrary because they're so disconnected from anything a human brain was built to process. After that comes RSGC 1-F01, somewhere between 1,436 and 1,530 solar radii, depending on which measurement you use, located in the massive open cluster RSGC1 in the constellation Scutum toward the inner regions of the Milky Way. This star is significant because it sits right at the edge of what theory says should be possible. The Hayashi limit, the theoretical ceiling on how large a red supergiant can grow before radiation pressure tears it apart, sits at around 1,500 solar radii. RSG C1-F01 is either just under it or right at it, within the margin of measurement error. It exists in a neighborhood of giants surrounded by 25 other red supergiants in one of the most extreme stellar environments in our galaxy. It's a star that tests the boundary. Then comes the current record holder, Stephenson 218, approximately 2,150 solar radii, located about 18,900 light-years away, also in Scutum. At that radius, if you placed it at the center of our solar system, its surface would extend past Saturn. Not Jupiter. Saturn. Every planet from Mercury through Saturn plus the asteroid belt, plus Jupiter's entire system of moons. All of it inside one star. Stephenson 218 doesn't just approach the theoretical limit, it exceeds it, at least according to current measurements. Either those measurements have significant error, or our theoretical models are missing something, or both. That ambiguity is uncomfortable and honest at the same time. And then there's WOHG 64. It doesn't fit neatly on this ladder because we're not sure exactly where to put it. It's outside our galaxy entirely, located in the Large Magellanic Cloud, about 160,000 light-years away. Its size estimates have shifted dramatically in recent years, from over 1,500 solar radii as a red supergiant, down to 800 solar radii as a possible yellow hypergiant, and then back toward red supergiant classification, again based on newer data. It's been brightening and dimming in ways that no star this size has done on human observable timescales. WOHG 64 is the entry on this list that refuses to stay still. It's not a settled fact, it's an active mystery. Now zoom out and look at all of them at once. What do they have in common? Every single star on this list is a red supergiant or a red hypergiant. Every single one is in the late stages of its life, running low on fuel, some of them actively shedding their outer layers into space. The biggest stars in the universe, the ones that occupy the most volume, are all dying. They got this large precisely because they're dying, because the exhaustion of their fuel caused them to expand outward into something enormous and cooling and red. They're also all relatively nearby, cosmically speaking. The Large Magellanic Cloud at 160,000 light-years is the most distant object we've discussed tonight. And even that is essentially our galactic backyard. The observable universe extends about 46 billion light-years in every direction. We've measured precise stellar radii across an almost incomprehensibly small fraction of that space. The Milky Way alone contains somewhere between 200 and 400 billion stars, and we have detailed size measurements for a tiny handful of the largest ones. What that means is that this list, the Sun, Betelgeuse, VY Canis Majoris, RSG C1-F01, Stephenson 2-18, WOHG 64 is not a complete ranking. It's the best ranking we can currently construct from the data we have. Every entry on it is subject to revision. Some of those revisions will move stars down the way UI Scooty dropped by more than half. Others might move stars up or introduce entries we haven't encountered yet. The night sky you can see from Earth contains roughly 5,000 stars visible to the naked eye. Betelgeuse is one of them. The rest of the stars on this list are buried behind dust and distance, invisible without serious instruments. They sit out there in the dark, enormous and unstable and burning through whatever fuel they have left. And somewhere out there, probably, is something bigger than all of them. Something we haven't found yet, waiting in the dark. When we started tonight, the sun seemed like a reasonable thing to think about. It's 865,000 miles across. It contains 1.3 million Earths. Light takes 8 minutes to travel from its surface to your eyes. By any standard you'd apply to daily life, it's an object of staggering scale. And then we spent the rest of the night dismantling that impression entirely. Stephenson 218 is 2,150 times the radius of our sun. If you placed it at the center of our solar system, everything inside Saturn's orbit would be swallowed. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, gone. All of it, inside one star. Our sun, the object that powers every living thing on this planet, would be a rounding error, a grain of sand dropped into an ocean. That's where we ended up. There's something genuinely strange about sitting on a planet orbiting an average star and knowing that. Knowing that right now, somewhere in the inner regions of the Milky Way, Stephenson 218 is burning. VY Canis Majoris is bleeding mass into the surrounding nebula at a rate that would be catastrophic by any scale we understand. Betelgeuse is somewhere in one of its pulsation cycles, its diameter shifting by hundreds of solar radii over months, its surface convecting in cells large enough to swallow our entire solar system. These things are happening now, at this moment, whether anyone is watching or not. Some of them may already be over. This is the part that tends to stop people. When you look at Stephenson 2-18, you're not seeing it as it is, you're seeing it as it was 18,900 years ago. That's when the light you're receiving tonight actually left the star. In 18,900 years ago on Earth, anatomically modern humans were still thousands of years away from inventing writing. The entire span of recorded civilization hasn't elapsed since that light began its journey toward us. And the star that produced it may no longer exist. The iron core may have already collapsed. The shock wave may have already blown the outer layers into space. The supernova may have already lit up a corner of the Milky Way with more energy than the sun will produce in 10 billion years. We won't know for nearly 19,000 years. There's no way to know sooner. The information can only travel as fast as light travels, and light takes 18,900 years to cross that distance. We're watching the past, and the present is permanently out of reach. WOHG 64 is even more extreme. Located 160,000 light-years away in the Large Magellanic Cloud, whatever we observe happening to that star right now actually happened 160,000 years ago. Homo sapiens had not yet spread across the entire planet when that light departed. Whatever WOHG 64 is doing in the actual present moment, we will not receive that information for 160,000 years. The universe doesn't operate on human timescales. It doesn't operate on scales that map onto anything we evolved to understand. And yet here we are, building telescopes precise enough to measure the angular diameter of a star thousands of light years away. revising those measurements when better data arrives, arguing in scientific papers about whether Stevenson 2-18 genuinely exceeds the Hayashi limit or whether our distance estimates are off, catching the first direct close-up image of a star outside our own galaxy, watching a star 160,000 light-years away change color over decades. That's actually remarkable. Not just the stars themselves, the fact that we can study them at all from this small, unremarkable planet orbiting an average star in one of the spiral arms of a galaxy, containing somewhere between 200 and 400 billion stars. Our sun, which once seemed like the obvious center of everything, turns out to be completely typical. Spectral class G2. About 4.6 billion years old, roughly one solar radius, which is, by definition, the baseline unit because it's the one we happen to live next to. There are stars out there that make our sun look the way a candle flame looks next to a 5-alarm fire. The numbers are real. The stars are real. And they were out there long before anyone on this planet thought to look up and wonder what they were. If this is how you want to spend your time, measuring impossible things, watching stars die from 18,000 light-years away, trying to hold numbers in your head that your brain wasn't built to process, then subscribe. There's a lot more of this to get into. But before you close this out, consider actually going outside. On a clear night, when the sky is dark enough, you can see Betelgeuse with your unaided eyes. It's the reddish star in Orion's shoulder, sitting about 700 light-years away. What you're seeing is light that left that star roughly 700 years ago during the early 14th century, before it began the journey across space that ends at your eye tonight. That star is 764 times the radius of our sun. It will explode one day, possibly within the next 100,000 years, possibly sooner. When it does, it will be bright enough to cast shadows at night and visible in full daylight. The people alive when that happens will see something no human in history has ever witnessed from this close. The rest of the stars you see, most of them, are places. Objects with sizes and temperatures and ages. Some of them are in the final stages of their lives. Some of them have already ended. The light reaching you tonight is old light, carrying information about things that happened long before tonight. They're not waiting for us to notice them, but I think it's worth looking up anyway.